This is chapter 19 on DC circuits. And this will be related to lab 5, which will be on circuits, parallel and series circuits. So we're talking about DC circuits, it's direct current. And what we mean by this is we have the simplest type of circuit is we have a resistor of some sort. We have a battery represented with that. And we have a current, I, that flows through the circuit, and the relationship between voltage and current is V equals I times R. Or voltage, that's voltage, this is ohms, and these are amps. All right? So that's the simple circuit here as far as that's concerned. So an example, if I have a 12-volt battery, resistance of 100 ohms, then I will be V over R, which would be 12 over 100, or 0.12 amps. All right? So that's what we mean by that. Now we talk about AC circuits. We'll get into that a little bit. We talked about that. AC, alternating current, we distinguish by that. This goes at generally 120 volts at 60 hertz. All right, so we talked a little bit about that back in chapter 18. We talked about power and alternating current, power and circuits, and household circuits. Okay, so what we're going to have here then, as we move on, and we talk about parallel and series circuits. So in parallel, so a series circuit is one where we have a resistor or a lamp, another resistor, and we can have more, and then it comes back to here. So this would be R1, this would be R2. When they're in series, you go from one resistor to the other without any type of junction in between. If I had something like this in between, then I'd have a junction, and this is no longer a series circuit. Because I'd have a short, it would pass, some of the current go through here, some would go through there. So in this case, there's only one current, I, and this is a battery. So this is a series circuit. As opposed to a parallel circuit, you know, series, you just go through and you have no choice but going through both resistors. In parallel, we'd have battery, and then we have one resistor coming back, and we have another resistor, R1, R2, and in this case, we have the current going through here, I, can be broken up into both of these. So we end up with I1 and I2, and in this case, the parallel means that the ends of both resistors are connected. One big difference between here, and this is why at old style Christmas lights used to be connected in series. But now all household things are connected in parallel. What reason I do this? Old Christmas lights, if one burned out, then that would stop the whole circuit, because if one goes out, the current can't flow anymore. So you'd have to go and try and check every single one for that to work. All right, that became very time consuming. I mean, you know, this is from 1950s and 60s, largely because it's more complicated making Christmas lights, which is takes less wire, but it's a lot simpler. In this case, if one goes out, the current can still all go through here. So in a parallel circuit, the voltage is the same across both. So voltage same. Current here, current is the same. Because it's the same current go through. What goes in here goes out here. All right? So that's how we have for that kind of circuits. Now, when we have series circuits together, and again, it could be 1, 2, 3, R, so let's put another one here. R would be R1 plus R2 plus R3. And so if each of them are, let's make it 5, 10, and 10, this would be 5 plus 10 plus 10. We could replace this with one resistor of 25 ohms. And again, we use the Greek letter omega for that. So in a series circuit, all the currents, the resistors add up. In a parallel circuit, and we can do a third one here since we're doing, and if R1 is 5, and this is 10, and this is 10. In a parallel circuit, if we were to replace this resistor, these resistors with one equivalent resistance, R, this R goes as the reciprocal. So it's 1 over R1 plus 1 over R2 plus 1 over R3. As long as all three, the ends are connected together, right? So this is connected to this end, connected to this end. So all three have the same, they're all connected together. It'd be like taking two resistors here, right? If I connect them like this, and that's connected in series, but if I connect them across like this, that's in parallel because the ends are connected. I can do a third one and so on. So these are connected in parallel. Now if I have a third one, while we're at it, say I take these two in parallel, that result can be connected in series with this one. So these two are connected in parallel, and the result is connected with series with that one. And we'll talk about that a little bit here too. So this is how you add resistors in series. This is how you add resistors that are all connected in parallel. And I'll leave that up for a minute. So an example here, this would be 1 over 5 plus 1 over 10 plus 1 over 10. That would be 2 over 10, which would be 4 over 10. So R, this is 1 over R, so we got to take the reciprocal. R is then 2.5 ohms. But you'll notice this resistance is less than any of the individual ones, which kind of makes sense because with parallel, the current can actually go through all three. So the overall resistance is going to be less, which adds to the overall current. So it actually draws more current. This is a problem you can have with a household circuit. If you have too many devices on one circuit breaker, you draw more and more current, as we talked about in chapter 18, that you end up overloading the circuit and break the circuit breaker. Okay. So that's the first few sections here, section 19.1 and 19.2. And I'm not going to do anything with Kirchhoff's laws per se, but what we're going to do is there's an example, there'll become examples Okay. And yeah, let's do this. So an example in the book. Okay. On section 19.2 related to Kirchhoff's laws, but it would be trying to analyze a circuit where you have multiple resistors and trying to figure out what the overall equivalent resistance for that would be. So, I'm going to take this example exactly as it is, and okay, so I'll sketch it up here. Because in the case you have either series or parallel, but if we have a combination of both, what do we have there? So the example in the 7th edition on page 532. And the only thing I'll make slightly different is there's a little resistor on the bottom. So I'm going to have is this. So I've got a 9-volt battery to this, which then goes to a 10 ohm resistor and a 6 ohm resistor, which then hooked into parallel with a 8 and a 4. Which are then connected together to a 5, which then ends up back here. All right, so what we have here, and this is exactly as the example in the textbook. You have the copy of the text, right? And what we have here are a combination of parallel and series. Now, you can add in series if no junction between are, okay, and in parallel if ends connected. All right, so that's the rule. All right, so what we have here, well, we have kind of a mess here. Well, look, are there any in series? All right. Well, we go here, we come around here. This 5 is, we go this way, and there's a there's a junction between this and that. There's a junction between this mess, and there's a junction here. So nothing here is connected. There are no 2 resistors that are connected with no junction in between. So this, we can't do anything here to start with. So you just do whatever, you do either one of these as you can. But we know it's these two, 8 and 4, are connected in parallel. So we can replace these two with 1. So that would be 1 over R, would be 1 over 8 plus 1 over 4, which would be 1 over 8 plus 2 over 8 is 3 over 8. So R would be 8/3. Let's see. Yeah, 2.7. Okay. So we will replace this with, right? So that's the first step. Replace this with 2.7. Okay. So you might want to write down each step, each one of these things, because again, I'm taking it straight from the book. The book is redrawing each one. I'm doing it now. Look, can we hook any in series? All right. Again, the 5 is not connected. There's a junction there. The 10 is not in parallel. It's in parallel with these two, but these two are in series because you go from the 6 to 7 with no breaking. All right. So we can replace this with 1, right? So we replace that mess with R. I'll call this R1, R2. That would be 6 plus 2.7, which would be 8.7. All right. Now we got 8.7. Now now we can see. Well, let's see. Is 8.7 is in parallel with the 10 because the ends are connected, right? The ends are, and so I can do that. I'll call that R3, right? And that'll be 1 over 8.7 plus 1 over 10 gets me something, and that is equal to 1 over R3. So R3, if you solve this, is 4.8. Okay. So I can then replace this, because they're hooked up in parallel, with 1 of 4.8. And then finally, these two are connected in series, and I can then replace all that with an R4, which would be 4.8 plus 5. So I can replace all this with 1, that is 9.8. And then that's the final resistance. So then the current, which I'll put up here, all right, so the current would be V over R, would be 9 over 9.8, or approximately 0.9 amps. So the equivalent current coming through here, starting with the original thing, would be that. So that would be the equivalent of all those resistors, is replacing that with 9.8. And that's how you do it. You take, if you can hook it, if there's any resistors connected with no junction, that's series. If the ends are connected, that's parallel. And that's basically all we're going to be doing for this, that. And we'll also be looking for, when we look at lab 5, talk about that tomorrow. I'll be actually going through this lab with you and doing that for you, which will talk about the same sort of thing. So that's basically difference of parallel and series circuits. It gets a little more complicated with that. We're going to skip section 19.4 on EMFs and go from there. Okay. And then, yep. All right. In the next section, we'll talk about, I'll leave that up, is on capacitors. Capacitors. So we talk about resistors. A capacitor is basically a battery. I have capacitors. Here's Here's our resistor we've had. This is an example of a capacitor, right? A capacitor is a thing, capacitor device for storing charge. And so like a battery is an example. A flash camera uses a capacitor because a battery stores the charge. I mean, this is basically a capacitor. It stores charge and then releases it. A battery releases at a relatively slow rate, so you don't use it all at once. And so we're going to talk about capacitors. Capacitors, we use the capital unit C for capacitance. So we define it as capacitance. And the units of capacitance are not, again, this is not coulombs, are farads. Right? And we generally use either microfarads. So this is 10 to the minus 6 farads. 1 farad is actually a very large capacitance. So we generally deal with microfarads, nanofarads, and so on. So make sure you keep track of your powers of 10 for prefixes as far as that's concerned. So, and part of I'll just give this to you because if you take the MCAT test, they have a tendency to talk about capacitance for some reason, but largely because maybe it's because the math and skills involved with doing that. So what we have here is, remember, when you have resistors in series, R is R1 plus R2 plus R3 and so on. And when resistors are in parallel, then 1 over R is 1 over R1 plus 1 over R2 plus 1 over R3. Now, capacitance, we have capacitors capacitors in series of parallel. It's exactly the opposite. We have capacitors in series. So if I take, where'd my capacitor go? So if I take 3 of these in series together, I'll hook them up, and again in series we do, and the symbol for capacitance are 2 parallel lines. So if I have C1, C2, C3 in series, it's 1 over C they're reversed. So in series, then that's the same as resistors in parallel. So this would be equivalent to 1 C of the same, okay? So if they're in series, this is what you get. And if they're in parallel, right? If they're in parallel, and I'll switch this. Okay. So that you have C1, C2, C3, this equivalent C would then be C is C1 plus C2 plus C3. Okay, so that's how that would work there. So it's actually opposite. So capacitors in series add reciprocals, much like resistors in parallel. capacitors in parallel, and just like resistors in series. So again, this is a series, whether it be resistor, in this case, capacitors connected in series, capacitors connected in parallel, the equivalent would be that. And we use the capital symbol. So again, the units are farads, and we're generally using like microfarads, or sometimes as small as nanofarads, which are 10 to the minus 9th. And nano is 10 to the minus 9th. All right. So that's the part on capacitors. All right, one more section here, then we'll just get a little bit of safety. Okay. All right. Okay, I'll leave that. All right, so what we have here then is now we've had resistors by themselves, capacitors by themselves briefly. All right. Now what we're going to do is look at if we have both of them together. So if we have a battery of some sort hooked up to a resistor, which is then hooked up to a capacitor. And we put a little switch here. Okay. And let's say R is 1 kiloohm and C is 1 microfarad, just for simplicity. Okay. Now, when we had just a battery, voltage, neglecting this, if you neglect the capacitor, just have a voltage with a resistor, and we measure the current, we measure the voltage or the current, measure the current in time, the current will just stay constant. We do not have, if you have just this kind of circuit with a battery and a resistor, the current will just be constant in time. Now, if you add a capacitor, the capacitor actually will build up charge on it. I mean, it's like charging a battery. You can run a current, you can charge a battery and eventually discharge, but that's how it all. So what we'd actually see here is if we start with this system, flip the switch, the current would start out at some value and then gradually decrease. This would be an exponential decay. Right? Because as the current is flowing through here, it's actually adding charge to this and creating a battery actually acts in the opposite direction. Eventually, this battery will be charged as much as this one is, and the current will eventually drop to 0. So this is exponential decay, and the way this works is then we can define the current. Here, I is a constant for just a simple circuit. For here, in this case, I would be I naught, which would be, this would be I naught, which in this case, I naught is V over R. So say this is 10 volts. And I naught, V over R, would be 10 over 1,000, or 10 milliamps, all right? But in this case, exponential decay, it'll go as T minus time over the product of R times C, where it turns out R times C is a unit of time in seconds, which would have to be because this has to be dimensionless. So this would be, time would be in seconds, and it would decay at this rate. And so in this case, R is 10 to the third, C is 10 to the minus sixth. So this time, what we call tau, would be 10 to the minus third seconds. And what does that mean? That means that in 1 RC time, it drops to 37%, or this value is I naught times e to the minus 1, which is 0.37. So after one time constant, it drops off to 37%. It drops off at exponential rate. So after one time constant, it would drop off to 37%. Now you can see the bigger this number, or this product, so if the bigger C is, or the bigger R is, this time constant can go much, much longer. If it's a very small number, it can go very quickly. So if it's very quick, so if you have a very small number, then it can drop very fast. And that's what we see there as far as that's concerned. So that's what we call discharging. So actually what you would do, now basically this now becomes a battery. After a period of time, this capacitor will start as a battery. You can use it, disconnect this, and use this to run a current in the other direction. So that's all we're going to be doing there. Again, the product, R times C, where you got to make sure you got the, make sure you get change the prefixes to the proper power of 10. You end up in this case 10 to the minus third seconds. All right? Okay, last section here is on safe wiring and stuff and how we do that. Okay, electrical hazards. Okay. I'll do this up in 1 minute. All right. Last section here. You can read this on electrical hazards, but generally what we have here is, a household circuit is 120 volts, right? That's quite a bit. This battery is 9 volts. It's a DC, AC, doesn't matter. So this battery is 9 volts. I could put my tongue on it. I'm not going to do it. You get a slight shock, but it's not going to. I put my fingers across. I don't feel anything at all. Now, if you do, so what we find, because we talk about what's dangerous, what's not dangerous. What is dangerous is not so much the voltage, as long as the voltage is less than about 20 volts. This is not harmful to anybody. But what can be dangerous is current. Current, dangerous. And this can be dangerous. Let's see, do we have? Yeah. We have current as much as, 1 amp. Current of 1 amp can be quite dangerous. If you have 120 volt, you put your fingers in a socket with connected to 2 wires, that could be very dangerous to you. As much as 1. So the limit for current is usually on the order of 50 milliamps or 0.05 amps is about the limit of that. So what's dangerous, what's not dangerous? 120 is very dangerous. If you have, say, a band, you get a spark, I see that like when you rub your shoes and get a little shock touching, just a shock there, and if you look at, that can be on the order of 5,000 volts. But the current is on the order of about a nanoamp. I mean, it's extremely small current. So it's a current that bothers you more than the voltage. You get a very high voltage, like a lightning bolt can be in the order of a million, several million up to a billion volts, which has very large current. That can be very deadly. But the body has an internal resistance to it of several hundred ohms. So if I put 9 volts across here, it's not going to hurt me. If I put this across this to this wire will get hot relatively quickly. Because there's almost no resistance to it. We'll get into that when we talk about AC current more later on. We talk about that'll be later, that'll be in the next test 3, exam 3. But for electrical hazards, the main thing there is to keep it there. Now, what you also have in a circuit is a 3-prong plug, and there's always the third one is always a ground plug, because what can happen is appliances can build up a charge, and if you do not have a ground plug, you can build up a charge onto it, and you can touch the device and get a big shock. So the ground is very important. A really good example is a helicopter trying to rescue somebody at land. So a helicopter flying and is trying to rescue somebody here. This helicopter develops a huge amount of charge on it. So before they can actually rescue anybody, they have to actually discharge by throwing a wire to water, to discharge it, and then they can rescue somebody. Otherwise, you could get a fatal shock from that. The people on there don't notice it because they're the same voltage as the as the helicopter itself. So somebody inside doesn't have any problem at all, but somebody outside would have a major problem. So you discharge it first, and that's what the whole point of a ground is, as far as that's concerned. Okay, and then the last section here is on measuring current. So this is section 19.7. And then the last section, finish up here, all right, 19.8. So I suggest you just read the chapter, read the handouts on this. I can talk about more than I do. But on 19.8, all right, measuring, if I have a circuit with a battery, a volt, right, a resistor, and I want to be able to measure the voltage and the current using my meters, like we've done. All right, if I want to measure current or voltage, how do we do that? Well, voltage is easy to measure, because what I could do is I put the voltmeter in parallel across the circuit. So if you are trying to check whether, say, a circuit works at a house, you can just put a voltmeter across the two ends using the volt and the common, put the two ends across, and then see if you actually have a voltage across this. If you have a voltage, then you have a current. So that's how you measure current, voltage. Now if you want to measure current, much like a gas meter or water meter, the meter has to be part of the circuit. Okay, I cannot measure current just by putting across it, because an ammeter has a very low resistance. If I tried to put an ammeter across this, because I'm too lazy to break the circuit up, all the current would go through here and would just break the circuit and would fuse. So the way you do it is instead break the circuit, put the ammeter in line, and then measure the circuit current. I did this with lab 4 because I had to take it out, take each one out, take one end out, put the ammeter in line, hook up the other end. So that's how that works for measuring current and voltage. And so that's what's important if you're ever going to do it. Voltage is parallel, you don't have to disconnect anything. Current is part of it, and you have to take it out and put it in line with it. So that's chapter 19.